Alright, the purpose of today's video is to give you a quick recap of how to use the limits to integrate what we call improper integrals. Now, there's a couple kinds of improper integrals, but for the purposes of IB high level in the core curriculum, or sorry, in the paper 3, really only concerned with improper integrals where one of the boundaries goes to infinity. Some of the others are where an integral passes over a gap or a discontinuity. Those kinds of improper integrals are easy enough to deal with, but we don't have to concern ourselves with those. The algorithm, of course, is simply to replace the infinity with a boundary a constant. Then we're going to take the limit as a approaches infinity. So all we have to do is take the antiderivative in this case, and what we're left with is an expression, negative 1 over a plus 1. So, easy enough, you let a approach infinity, oops, I got ahead of myself there. You let a approach infinity, you get 0 here, so it's 1 minus 0, or 1. After I take the limit, notice the limit symbol goes away and we're just left with the number. So what that means, if we look at it graphically here, is that if we start from x equals 1 and we look at all the area under the curve, forever and ever and ever, amen, for infinity, there is in fact a finite area, and that area is precisely 1. I find that extraordinary. First of all, that the area is finite, second of all, that it's perfectly 1. So that's what happens when you have the function 1 over x squared. It's a nice little function. Check that with Wolfram Alpha just to be sure. You could actually enter in the entire integral and it'll work it out for you. Become a member and I'll show you step by step. Or you just watch my videos. I'm going to do the same thing, except this time we're working with 1 over x. Seems like the same kind of graph. It's had the same kind of behavior. It's got to have a finite value too. When I integrate, however, and then I take the limit, I see that I did not get a function that is bounded. Basically, if I let a approach infinity, the natural log of a also approaches infinity. Just take a little longer, but it'll get there. So, this is a divergent integral, and the integral does not exist. So where 1 over x squared has a finite sum underneath the curve, 1 over x itself does not. And that is verified by Wolfram Alpha saying, integral does not exist. Thank you, Wolfram Alpha. And this function looks just like the other ones. This is the reason I chose this one for the video, is to make the observation that 1 over x squared plus 1 looks just like 1 over x squared, which we worked with earlier. However, when we look at the graph, there's no asymptotic behavior. The other difference here, of course, is we're going from 0 to infinity. So I wonder how this is going to turn out. It'll take a little while for you to recognize the fact that this is actually arctangent. So when I take the limit as a approaches infinity of the arctangent of a, turns out, sorry, this, by the way, the arctangent of 0 is 0. Turns out that if we allow a to approach infinity, the arctangent of infinity is in fact pi over 2. Remember, the tangent of pi over 2 is infinity, so the arctangent of infinity is pi over 2. Another way to look at it is if you look at the tangent graph, it has a horizontal asymptote at pi over 2, telling us the exact same thing. So, this one took a whole different turn. All of a sudden now we're working with arctangents and pi over 2. Now working with the cosine. This one is only interesting because if I look at the area, as I continue to go on from 0 to infinity, I have chunks above and chunks below. So maybe when I try to integrate, they're going to subtract out and we just get a total of 0, a net 0. However, when I observe the antiderivative and we allow a to approach infinity here, well, the sign of 0 is easy, but we let a approach infinity, I can't do it, because the sign goes up and down, forever and ever and ever, and here again, Wolfram agrees, the integral does not converge. So, that's integral language telling us something that our intuition might not be able to really wrap our heads around. Alright. For our last example, and I'm sorry I'm going really quickly here, this is more of a, sort of a quick little recap, like I said. Here, I recognize that this is a function that exists, the product of two different functions, e to the negative x and x. Whenever I see the product in an integral, one of the things I think of is the old integration by parts algorithm. That hasn't left us yet. So remember, when I do the integration by parts algorithm, what I have to do is choose one of the two functions to be differentiated and one of them to be anti-differentiated. Since e to the negative x is easy to do in both directions, I'm going to choose the value for u to be x, because when I differentiate it, it goes down 1 power, so that's a good thing. And then when I go anti-differentiate e to the negative x, it'll be negative e to the negative x. just great. Another negative to worry about dropping. So, continuing on then with the algorithm, this is u v prime. So the integral of u v prime is going to be u times v. It's u times v. So notice, because it's a bounded integral, when you do the integration by parts algorithm, we then do our fundamental theorem boundary evaluations inside. So here I took the limit as a approaches infinity of all this stuff with the boundaries, and then I continue to subtract the integral from 1 to a of v prime, or sorry, v times u prime. That's something that is easy enough to integrate. First we'll extract the negative, so we get something a little bit nicer looking. Actually, no, I didn't extract the negative because I knew the antiderivative was going to get rid of the negative itself. I apologize for getting ahead of myself. We continue on then. Here, evaluating this portion, fundamental theorem of calculus there. Evaluating this portion, evaluating that portion, cleaning it all up, doing some cosmetics. I would encourage you right now to pause the video. Rather than me go through it, just take a look at what happened. Try to see if you can simplify for you're on your own on separate paper, or follow along with what I did right here. Carrying on though, I just do a little bit of mathematical cosmetics and I end up with this expression right here. Now, the limit as a approaches infinity does not affect 2 over e, so that constant is going to be pulled out. So I'm going to have 2 over e plus the limit as a approaches infinity of a minus 1 over e to the a. Intuition tells us that e to the a is going to increase way faster than a negative a minus 1. However, just to prove it, we're going to first extract the negative and then apply L'Hopital's rule, where I take the derivative of the numerator and the denominator. That enables me to then allow a to approach infinity and confidently say that this does equal 0. Therefore, 2 over e is the value of this improper integral. Thanks for watching.